accepted.
I think that means we're on. Yes, and we have audio. Welcome. Everybody have a good lunch? Nice. Okay. This can be the session, as you know, right after lunch, where people get sleepy, and there's some lights on me, but they're not bright enough for me not to be able to see. So I'll help you stay awake. We're going to talk about Apache Pinot. My name is Tim Berglund. I work for a company called Startree. Startree makes a managed service that's like a fully managed Apache Pinot in the cloud. And this talk is something of an introduction to Pinot, but with a special emphasis on why is it fast? And more to the point, why does that matter? Not that any of us really intentionally chooses slow tools, but let's dig in. Was there a question? Was there a question? No, all right. Pinot's a real-time analytics database designed for the world of streaming. The typical case is for Pinot to be connected to Kafka to ingest events from Kafka or Kinesis or Pulsar, but it ingests events from some system and makes them queryable. There are various ways to get batch data into Pinot. We'll talk about that. But that's really what it is. It's a real-time analytics database. Now, that requires a bit of explanation. But we might ask, who is involved with Pinot? I work for this company called Startree. We're involved. Pinot was created at LinkedIn just a few years after Kafka. They had transitioned to this event-driven architecture. They were really one of the early adopters in terms of mainstream web or information technology shops doing that kind of thing. They were leaders in that space, and they discovered a little while after this transition and had been building Kafka, they also needed a database that would behave sort of like Kafka, but be an actual database. So they started building it in about 2015, originally to power the Who Viewed My Profile feature. I don't know if you remember when that showed up, sort of a narcissistic little piece of technology, which means I love it, but that was not batch data, right? They designed that to feed things in real time, to tell you in real time who had just viewed your profile. And that's a premium feature now, I think, oddly enough, but it certainly wasn't back then, because they were trying to take LinkedIn and make it from this kind of static resume site to something more like a social media property that you'd want to visit all the time. Uber is also a primary contributor to Pinot. We'll get into some use cases there. Those are basically, you got Startree, Uber, LinkedIn. Those are the big contributors, and then, of course, a few dozen other organizations that also make contributions. I think a more fair question is why make a new database? We don't stop doing that, right? We're always making new databases, but there needs to be a reason. Like, honestly, there are a lot of ways to do analytics right now. A couple of years ago, so I work in developer relations, and sometimes people call me and set up calls and say, hey, can you tell us about how to build our DevRel team, early stage companies and things like that. And a couple of years ago, all of them were analytics startups, right? Now, of course, we know for any startups being formed right now, obviously they're going to be AI startups if they are self-respecting people. But a couple of years ago, everybody was an analytics startup. There's a lot of ways to do this. Like, what's wrong with Spark, Snowflake, DuckDB, right? Those guys tell me we don't even need big data. We just your laptop fast enough, and that's fine. And what does this word real-time mean anyway? That sounds marketing-y. Well, let me give some examples of that help illustrate the why before we get into the how and the technical details of how Pinot works and how it thinks about performance. This is a screenshot from yesterday. I looked for sushi near my hotel. I'm just staying at the Q Plus right across the street there. And this is Uber Eats. So again, Uber was one of the first adopters. And those things right there, those delivery times, you zoom in on those are calculated in real time from actual delivery events happening here. So there's a geospatial component to the predicates. There's a keyword. I asked for sushi, and those deliveries are actually being aggregated in real time and delivered to me in the app. Now, when I do a search in a meal delivery service, I do sort of expect that to load quickly, right? I'm fundamentally synchronous when I'm doing that. I'm looking at my phone, waiting for a result. So when we say real time, I don't want you to think that just means, wow, it's really fast, because that's not helpful. I started my career in firmware, and in firmware, often real time means there's some bounded latency, right? Like you have 3 milliseconds to process this event, or somebody dies, or whatever it is, or something breaks, or it's just the system is incorrect. That's not what this means. What I encourage you to take away when I say real time is this can be done synchronously while I'm looking at it, so it is in the user interaction layer, which is not where analytics queries normally take place. They are normally populating dashboards, and if they take 15 seconds, that's fine, because the dashboard only needs to refresh once an hour, and the business analyst or the executive is perfectly happy. I'm not going to wait 15 seconds for delivery times to populate on the screen. I expect them to happen right away. So typical query latencies that you see in Pinot for things like this that are feeding features in the user interface are going to be under 100 milliseconds. Sometimes significantly under 100 milliseconds. Like I've seen actual P75s of like 15 milliseconds in stuff that Startree is doing with customers. Crazy times for an OLAP query. Another use case, like I said, it was originally developed for LinkedIn. In 2015, LinkedIn didn't look like this. This was before it really had become a social media site. But all of these things, current number of impressions on my posts, how old is this query here, or pardon me, this post here. The fact that this post from Chris Jenkins was even showed to me is a Pinot query. There's analytics happening, looking at what I've recently seen, what people I'm heavily connected to have liked or commented on recently. I mean, you kind of know how feeds work, but this all happens to be powered by Pinot on the back end. Those stories, number of comments, all this stuff on the page these are all Pinot queries happening on page load. So when I say real time, I mean when I'm tapping on something on a mobile device or page load is happening, I am sitting here as a synchronous human being waiting for the user interface to respond, and it doesn't feel slow. So that's still a somewhat squishy and subjective definition, but honestly, I would rather that because you can wrap your mind around it, and it doesn't just mean, well, it's real fast, because that's, again, not a helpful definition. This is a particularly concrete kind of use case, and this is the reason why Pinot exists, for analytics that face the user. And that's a big change. Historically, I mean, when analytics started, right, those were printed reports. Or maybe when analytics really started, maybe they were punch cards that somehow got turned into something human readable. But in the modern data warehousing era, going back to the late 80s, early 90s, printed reports were what you wanted. The web happened, that just turned into dashboards in a browser. That's where analytics queries have traditionally gone. Pinot is now looking at sending them to users. So that same data that you want to show to an executive or a business analyst in a dashboard, we're going to take and make into a feature and expose it to the person using the app. Key difference. I know I've said it like 4 times, but it's a big enough change that I want you to make sure that, I want to make sure that you hear that. That is the Drax asking why Pinot. That is why Pinot. And there's a little more than just that, right? Things are a little topsy-turvy right now in the way we build systems, just in software architecture in general. The modern data warehouse is something like 35 years old. It's kind of old enough to maybe start seeing some gray hairs and needing to adjust its diet and things like that. You know how it goes. Just a few years before that, that modern data warehouse was a response to a change in software architecture a few years before that, and that was the client-server paradigm. Okay, that dates to the 1980s. And a lot of you in this room were alive then. Maybe some of you weren't. So this has been an extremely stable paradigm that survived even the web, all right, until recently. Typically, the way we build applications even if we are a so-called digital native and serving the web, we've built monoliths, right? And those are essentially client-server systems. Now that that's kind of dead, or it's not dead, it's showing it's under threat and under stress. Now we have this new system where we have, say, Kafka at the bottom and all of these microservices communicating using Kafka topics, and a lot of confusion about what goes on in between there. Put a different way, here's some microservices talking over Kafka. Kind of doesn't matter what the system does. You've probably seen a diagram like this before. This is sort of the way things are typically being built now, new designs, and the system of record is gradually migrating to be the events in those topics. And that's really cool as a way of getting these services to talk to each other, but there's a problem there, which is it's very difficult to know what just happened inside the topics. In the good old days, which were not so good, when we had a single database and a monolithic application around it, you could just go look at the database and figure out what's true and what happened. Now I have topics which I can scan, but I can't really query. So there's two motivations here for Pinot. One is the whole set of consumer expectations that drive us to need to do things in real time. The other is we actually build software differently now than we did even 5 years ago. And that is enough of a disruptive paradigm. Like maybe as you've experienced microservices, it's seemed like a pain and hard at first, and we've all made mistakes, and then we kind of figure it out. It's getting to be a more stable and accepted way to build things. But a lot is disrupted, maybe more than you realize, and there's all kind of infrastructure in between your code and Kafka topics on the bottom that is now up for grabs. And the other motivator for Pinot is to be in there and to make it so that you can see what happened in Kafka in a way that is consistent with the real-time character of the rest of the system. So I could dump all those topics to a data lake and run Spark over them, but that's, again, not what we're talking about. We're talking about things that need to happen now. All right, a couple of other terms I want to make sure I'm super clear on, and I think probably most of the people in this room could give a good definition of these things if I asked you, but I've mentioned analytics. I haven't really mentioned its opposite, and that is a transactional database, and I'm going to define these things as a key difference. A transactional database is usually focused on a thing, right? You want to create, read, update, delete. There's some entity. Now, transactional databases can execute other kinds of queries, but they're basically optimized to look up a thing, write a thing, create a thing. You're generally focused on a row or an entity, and it's typical for you to change things. You're probably not going to scan large amounts of things. In an OLAP database, you're usually focused on many things. And instead of CRUD, create, read, update, delete, you really tend to focus on ingesting and then querying. Large scans of lots of stuff are typical. That's more often I'm going to scan many values of one column. And mutations are possible. They're not always normal, right? These are typically events now that I'm looking at. Events are immutable things, so usually when I ingest them, they stay the way they are. There are, of course, some kinds of events that represent mutable states of affairs, so we would want a good real-time OLAP database to handle basically upserts. But those are going to be generally the exception. So we want mutations to be possible, but they're not typical like they are in OLTP. So really, just think of it, the difference between the one thing and the many things. Like we take a look at some data here, some nice personnel records, jobs, locations, ages. OLTP would just want to see, let's go visit Ava. Let's see how old she is and where she lives and what her job is based on her ID. Whereas in OLTP, I might say, well, I want all of the DevRel people. So let me filter that data set to all of the DevRel people, and then I'm going to scan through their ages. I want to read all of the ages and compute, say, an average or whatever that happens to be, average or min or max or whatever aggregation I'm doing. But I will look over all these records, filter, and then scan. Scanning becomes, the title of the presentation is Pinot, Why Are You Fast? scanning becomes the rate-limiting function in an analytics database, and in a real-time analytics database, there's tremendous pressure to be able to get these query times down under 100 milliseconds with very many concurrent queries, right? With potentially tens of thousands or hundreds of thousands of queries happening at once if you're something like LinkedIn. So how do you win? How do you do this? Well, I hope this is not disappointing. There are 3 things you can do. Scanning is your rate-limiting thing. Well, so number 1, you can scan faster. Number 2, you can scan less. That's even better. If you can just avoid scanning altogether, that's the fastest scan you'll ever do. And of course, you can parallelize scanning, right? You can make this a distributed database and move all that stuff. So these are the 3 themes I want you to keep in hand. Scan faster, scan less, scan in parallel. Scan faster, scan less, scan in parallel. I'm going to walk you through the basic architecture of Pinot, look at the indexes, some of the index types Pinot supports, and if we have time, we'll talk about a kind of a future optimization that's being built in Pinot right now to make a particular kind of query work better going forward into the future. So scan faster, scan less, scan in parallel. Let's walk through how Pinot is built and see how these things show up. So there's going to be a relentless focus in the engineering. There is a relentless focus in the engineering of this thing to pick which one of these 3 things we're doing at any given time. Scanning faster, scanning less, scanning in parallel. All right. I think the best way to explain how Pinot is built is to follow a record being ingested. So we're going to start with this little piece of JSON. It's clickstream data, and that's a perfectly valid kind of event to ingest into Pinot. One of the neat things about Pinot in this space of real-time analytics databases is it doesn't seem to have like a native or favorite use case, except maybe meal delivery. Like, I don't think you can get a meal delivered on planet Earth without Pinot being used. For whatever reason, that just really worked. I don't think there's anything architecturally about Pinot that makes it suitable to meal delivery. It just doesn't. Things don't work that way. But yeah, we got meal delivery, and there's financial things, there's social media things. I can think of a actually not gross ad tech application that's Pinot powered. It's kind of all over the map. I'm just going to use a click, and we can stop looking at that JSON right now. I want to ingest that into a table because that's stuff Pinot looks like an ordinary relational database. So as I do that, now there's 2 ways to ingest data. There's think of it as batch and streaming. The terms, unfortunately, are offline and real time. And as we know, naming things is hard, so let's just go with batch and streaming. I think I like those words better for now. So we're going to go through batch ingestion before we talk about streaming ingestion. And right off the bat, one of those 3 things, scan faster, scan less, scan in parallel, one of those is being enabled in the way this works. So as we're ingesting batch records, or records from some source file, those are ingested into files called segments. And a segment is a bundle of a few files, but it's just easier to think of it as a file of maybe a few hundred megabytes. And that segment contains, you can cut it off at a certain size, a certain number of rows, whatever it is. As we ingest more and more records, we create more and more of those segments. And a table is composed of this collection of segments. Now, those segments, we're going to dive into how those are structured, but you're probably thinking already, I bet I could put those segments on multiple machines, right? So that will enable us probably to scan in parallel. So right away, with a segment structure, we've got one of our 3 pillars of what makes Pinot fast. Another one shows up in the structure of segments. So if you have not spent a lot of time thinking about databases, I was, a long time ago, around the time that the first data warehouses were being built, a computer engineering major. So I took a lot of hardware design classes. I did not take a database class. I never took compilers. This is stuff I had to learn on the job later on. So if you're a person who never took a database class and haven't thought about this, And you just think, well, okay, I'm ingesting this row. I should probably serialize the bytes of that row and write them to disk, right? That's what a normal person would do if you were building a transactional database, because a transactional database is oriented around that row, that one thing that you want to change or read. That's not what an analytics database does. In the OLAP case, what we're going to do is take all of the columns in the whole segment, say there's 100,000 rows in this segment, all 100,000 IP addresses, we're going to write them together. This is a column-oriented database, and this is a typical storage structure for a database that's optimized for analytics. All 100,000 user IDs. Looks like user ID has an index. We'll write that index in there. All 100,000 remote user values, whatever those are. Time, more indexes being written, request, status, number of bytes, an index for that, the refer, the agent, all of those fields in the input data, we're kind of batching up the values and writing all of those column values together, which helps us later on when we want to scan through one of those values, they're all together on disk, or whatever the storage medium is. They are contiguous. So now I'm going to be better able to scan those values, which means I am scanning faster. Instead of either seeking, if for some reason I'm using a spinning metal hard disk, or doing lots of scattered block reads all over the place for an SSD, I'm now doing some contiguous block reads. So I am scanning faster because of the way segments are designed, because it's column-oriented. All right, and we got lots of segments. Tables can get big. Who knows how many of them there are. And in Pinot, we write those to a component called a server. And I said naming things is hard, so it's okay. There are other components in there that are also presumably running on something we might call servers, but there you are. We put those segments on a server, and other segments on other servers, we're able to scale that out. So this is, again, how we can now parallelize our scanning. Servers are where the data is stored fundamentally, and this is where actual query compute happens. You've got a high bandwidth connection between a processor and SSDs over a PCI bus there in that machine, and so the bulk of the query processing is happening on the server for whatever segments. A query may implicate many, many segments. We sort of don't know how that works yet. We haven't built that out. But for whatever segments are implicated on a particular server, that compute is happening locally, and we're able to do that faster because the compute engine and the storage engine are tightly coupled. So that's a second reason why we are scanning faster. We're scanning faster because it's column-oriented and because compute and storage are tightly coupled. Servers are the things that do the bulk of the work in Pinot. There are going to be probably more of them than any other component. Segments can be kind of offloaded when they get old and put in the cloud in open source Pinot. That's not, properly speaking, a storage tier. It's more like a backup for old data. That's a way to spool off some of that data into the cloud. The way you actually make queries happen is there's a machine called the broker. There's going to be a cluster of brokers. This is another thing that there could be many of. And the broker knows, based on the predicates in the query, what segments are going to be needed to answer the query. It's got all that metadata available to it. So it's going to be able to say, okay, this query looked at it, and it needs segments 2 and 8. So I'm going to scatter that query to server 2 and server 3 because I can get at segments 2 and 8 there. So again, we have scanning in parallel happening here, because you really could, if you look carefully at the diagram, 2 and 8 are actually available both on server 3. But if I scatter some of that to 2, then I've got both of those scans happening in parallel on those two servers. There's another machine called the controller, a high availability cluster of machines called the controller. That's a cluster manager that's making sure brokers are up and running and segments are available on servers the way they're supposed to be with all the metadata existing in Zookeeper. That's just all kind of back-end architecture stuff. And clients are issuing queries to brokers, and there you go. And there can be ingest happening all the time. This is less a why Pinot is fast and more architectural detail that I think some of you would be upset if I didn't share. So let's talk about streaming ingest, since the whole reason Pinot exists is because streaming exists and we want things to happen in real time because the rest of our systems are event-driven. We just talked about batch ingest. That goes into what I was calling this batch table, or what Pinot calls an offline table. Regrettable name, because in fact you can query offline tables as much as you want, and they're perfectly available, but these are just things that are the result not of streaming data. As we do that, like I said, we're building up these segments. Real-time ingestion is a layer on top of that. So in real-time ingestion, we've got this thing called a consuming segment, which is an in-memory data structure, and as we're consuming messages from Kafka, Pinot is a native Kafka consumer. There's no Kafka connect or anything like that. As soon as a message is consumed, it's written into the offline segment, or pardon me, the consuming segment, and is immediately available in query results. And in the typical case, when the consuming segment fills up, it gets written to an offline segment on disk. There's a hybrid real-time offline table where the consuming segment fills up because it is in memory and gets dumped into a segment on disk, and the queries can be answered from both places, from the segments that are statically on disk and for the current consuming segment that's being filled up. So there you go. That is how we get data into Pinot from Kafka, and let's talk about indexes. The fundamental purpose of indexes is to scan less, right? These are the ways that we want to figure out in a time-efficient way to not have to read as many columns. And backing up on that, I want to make sure that point was clear because that's a very opinionated way to look at a query. I can use Pinot to simply fetch rows, right? That's okay. If I've just got stuff out there in the database like readings from smart thermostats, I can just get those readings. I don't need to compute an aggregate on them. If I've got 1,000 readings for the day from some particular sensor in some particular building, I can just fetch those and have them and process them in my application. But typically in the analytics case, in the OLAP case, what we want to do is we want to take those 1,000 things and, with respect to some measurement, some probably numeric column value, run it through a reducing function of some kind, right? Sum, average, min, max. There are a couple dozen others that are available in Pinot that are sort of the usual suspects, right? Some statistical functions and some hyperlog log counts and the things that you might expect to see. They're all in the docs. So typically what I'm doing is there is some column I'm interested in, and we'll call that our measurement, and I want to get lots of those, for whatever lots might mean, and squish them together through some reducing function and get a result back. That is a common thing, like you saw on the LinkedIn page and on the Uber Eats page and on any other meal delivery service, in particular the average delivery time. That's like the most visceral, easy one to understand, especially not right now because it's right after lunch. Who cares what delivery time would be, right? If this were before lunch, you'd be like, yes, delivery time, pressing existential question, when can I have my food? The whole idea behind indexes is to make it so that we're not scanning much. Scanning as little as possible. Scanning less is the best kind of scanning. So here is a view of actually most of the indexes that Pinot supports, and we're going to go through these and just kind of talk about what they do, because they're all kind of cool and help in different ways. Now, the forward index is kind of like a way of saying, okay, where is row X? Because remember, columns are all stored together. I can't just go somewhere in a segment file and get a row. But if I know what row I want, and there's a forward index on that column, this lets me seek quickly to that part of the segment file and get that column value out. Remembering, though, that this is a column database and rows are scattered everywhere, again, the real question is, where is this column for this row? This is an index we build on a particular column just to fetch the value of that column. And since rows are scattered everywhere, we may not even have to have a primary key defined. Internally, there's a thing called doc ID. So I have some illustrations of the indexes, and I have a thing called doc ID, and that's just Pinot's internal identifier for a row. You can read it, right? You can get it out of a query, but it is not a thing that you create when you're ingesting data. Fun fact, by the way, about Pinot and inserts, the insert statement. It recently added support for the insert statement. You're thinking, hey, nice, okay, I can write data. I mean, historically, typically people get data into Pinot with Kafka, right? So you set up in the table config, you point it at the Kafka cluster, tell it the topic name, define the schema, and ingest data. If it's a batch job, there are various ways of creating those. There's a command line tool that you can use to ingest data in various formats, the usual suspects from S3, from the local file system. You can use Spark to create segments. There's an API to do that. In none of those cases are you using a SQL insert statement to do this. The insert statement in Pinot is just a way of defining one of those jobs. So instead of using command line ingestion utilities, you use a statement that's called insert, and is a highly customized version of insert that really just begins an ingestion job. Anyway, the forward index, the way it works, that data that you see there with those three cities, Littleton, Mountain View, and Prague, the numbers, so I'm just showing one column of that table. The numbers are the doc IDs. That's the internal hidden doc ID, and this is just one thing, and so doc ID 0 points to Littleton, 1, same city, 2 is Mountain View, 3 is Prague, 4. So that's what the forward index would do. This particular column would also be a dictionary encoded column, so it would actually be stored that way on disk. You would only store the unique values. You don't store a separate copy of the string for each one. Now we could flip that around, the doc ID and the location, and we would have the inverted index. The inverted index answers the question, what rows does a particular value occur in? So you get a value, and it gives you a list of doc IDs and lets you efficiently get those things out. So same data, now though the term is on the left, and if I say, hey, where's Littleton, 0 and 1, where's Mountain View, 2 and 4, it just gives me those things. So if city were in the where clause, it was one of my predicates, and I specified Prague, well, I'd have to do a lot less scanning. So I'm scanning less. Range index. Okay, this is kind of cool. This is like a customized version of the inverted index. The inverted index, I give it a value, and it gives me doc IDs, and I'm doing the same thing here, except I've got some numeric measurement column, and I'm going to chunk that up into ranges. So I'll give you an example in a minute. When you're building the index, you can specify how many range chunks, like you want 100,000 different range chunks and up to 100 rows in each one, or something like that. You can specify these things as you're building the index. Because you don't want, on the one hand, you don't want too many ranges, because that's going to be a problem with space in the index, but you don't want too many elements in each range chunk, because the whole idea is to, again, scan less. So it would work something like this. Again, I'm limiting the view of the data. This is just doc ID and some measurement. And with those values and ranges defined in this nice convenient way, I would say, oh, if it's between 10 and 20, that's just that one doc ID, 3. And this is pre-computed, and so I get a super quick way of limiting the amount of scanning I'm going to do with a range index. We're going to come back to range index in a minute, because there's another cool thing we can do with it. There's a Bloom filter index. So if I've got some column where I will be performing equality predicates. So if city equals Littleton, or city equals Prague, or something like that. So it only works for equality predicates. The Bloom filter is an in-memory data structure that probabilistically gives me an indication of whether I should bother looking in a segment. Okay, so if the Bloom filter index says no, Littleton is not in this segment, we can just prune that from the search. Because when a Bloom filter says no, it means no. When a Bloom filter says yes, that means probably yes. And so what the query engine will do now is actually go scan in the segment itself to see if that bears out. So Bloom filter says yes, it's probably yes. It says no, it's definitely no. And this is an in-memory data structure that is super quick to access. Only works on certain types of columns. Let's look at text. So a query like that, where there's some text column that's a big text blob, and I want some kind of search expression. Now, an exact match term query, if you were looking at the inverted index, you could do something like that, right? And I gave that example of city. City would be a string field, not a big giant text blob. But if it were a text blob of longer unstructured text, usually you want other kinds of things, phrase searches, fuzzy matches, regular expressions, and so this does that. It's like a little embedded Lucene inside each server, inside the column, you could almost think of it, where I can do queries like this in a performant way. There's a geospatial index, perhaps unsurprisingly, given Uber's involvement. And they had their geospatial library that divides the world up into a bunch of hexagons, like a giant role-playing game. I like it. And there is, frankly, this is worth its own talk, which is why I have the docs link on there. Like, if you're interested, you should definitely go read the docs. There is a library of several dozen functions that you need to have mastery of to have complete control over this index type when you're defining predicates, and very powerful index type that gets used in production widely and gets lots of attention. So worth looking into, but I'm really just kind of flagging it now. This is a way of again, scanning less with geospatial predicates. There's a JSON index if you've got complex JSON data, potentially nested JSON in a field. So I was showing us ingesting JSON data, but this is where one column is some kind of potentially complex JSON object. I've got, the usual suspects options for defining predicates in terms of those objects. I can nest array and object accesses in arbitrary ways and get performant reads of those things. The timestamp index is an extension of the range index. So you've got a timestamp field, and every Pinot table has to have a date and time defined. Pinot never describes itself as a time series database, and I think it's misleading to call it one because the family of index types are a little more interesting than you typically see in a time series database. Yet you can't have a table that doesn't have a time. So it's complicated. The timestamp index works like the range index, and the ranges are equivalent to what you might know as grain in traditional data warehousing terms. So if I have a timestamp column, and that's second resolution there, but I am interested in finding out what happened on a particular day, then I'll build a timestamp index with day grain. And it's doing basically the same thing. It's truncating that timestamp at just the day and building a range index accordingly. So do that same thing. And then there is the vaunted star tree index. So not to be confused with Star Tree, the company, right? That's the name of the company I work for. We make a fully managed Pinot. It's great. We have a DevRel team that I love because it's mine. This is an index type in Pinot that predated the company. So what you have here is if you have an aggregate that you want to compute, and there's always the same set of predicates, and you want to use some number of them in the same order. That seems like a lot of constraints, but this is a way to scan less by aggregating in advance. Show you how it works. Okay, here's a data set. So this is ad impressions. That's the actual data. We have 3 dimensions: country, browser, and locale. Okay, I might sometimes just want country to be in my predicates, in my where clause. Everything in Mexico. I don't care about browser, I don't care about locale. Sometimes I might want country and browser. I want all the Firefox in the United States. Sometimes I might want all 3, all the Firefox in Spanish in the United States. What are those impressions? So you can see how those are going to aggregate. So I define the aggregation that I want to compute, let's say sum, and the index builds a tree like this. This is the structure of the index itself. And I know the type is too small to see there, but you can have the aggregation of the whole thing. That next row down is country. So if I just say, what's Canada? Well, that's 600. I didn't have to go and scan all of the Canada rows and add them up. The index contains the aggregate. So this is the only time pre-computation meaningfully is happening in Pinot, only with an asterisk. Pinot doesn't get its performance by pre-computing, except in the case of the star tree index, which is why star tree index performance measurements look fake. It just looks like it's, somebody's making the number up, because you're really just doing an index lookup and you never have to go back and read the segment again. If I go down through and say, well, I want Canada and Firefox, then I go 2 levels down on the tree. If I want, well, I don't know what country, but all of the French locales, I can, navigate down the tree and find that and get that pre-computed number out of there. Creates all of these documents in the index, right? So it's going to be this big explosion of things I dump out there, but that's how it works. Okay, that's it for indexes. Indexes are all about scanning less. The segment format, the format of the data, is about scanning faster. The fact that I can distribute my segments over many servers is about scanning in parallel, parallelizing that scanning. But this architecture bites us in one way, and this is a thing that in just the few minutes left I want to talk about briefly, because the thing being worked on right now, and in Pinot 0.13, the current release, it is available for, not recommended for production use, but some cowboys are sort of doing that, and people are testing it and getting it figured out, and that's multi-stage queries. Okay, here's a join. 0 people should be upset by this. It looks like I'm joining a table of baseball statistics to a table of baseball teams. Now, those are different kinds of tables, and they're going to be different sizes, right? The stats, in data warehousing terms, we're going to call a fact, right? That's whatever each pitch, hit, throw, injury, I don't know what kind of stats are in that table, everything, right? It's huge. There's all these events in it. There's a lot of facts. It's a good thing we have Pinot. Teams, well, there aren't too dang many of those. That's a dimension. That's reference data, right? And the way this works in Pinot now, prior to the multi-stage query engine, is you have this super goofy syntax, right? You don't even call it a join. You're calling it a lookup, and the baseball teams table, in the table config, you actually define that as a so-called dimension table. That's a hint to Pinot to say, this is very small, and you can put a copy of it on every relevant server. It's small enough that that's okay to do. So when the server, because remember the server is where the storage is, tightly coupled to the compute, which is another way we scan faster, the server has every dimension table, and so you can just do that in a tightly coupled, fast way running on the PCI bus between the processor and the SSD drive. So the syntax is wonky. There's a limitation, but you can kind of join with fact and dimension and that crazy thing, you know. But let's make this a little harder. Let's say I've got a smart thermostat network, my favorite real-time example, and I also have traffic data. And I want to get on an episode of the Freakonomics podcast with something about some correlation between traffic patterns and the way people's thermostats work. So I need to do this analysis in Pinot, and for some reason it needs to be in real time so people can explore it on the web. Examples are not always easy, but work with me here. So I've got thermostats, the thermostat readings, all my smart thermostats reporting in every 10 seconds across the whole world, and all this traffic data from real-time sensors coming in also. Both these coming in from Kafka feeds. They're both fact tables. They're both big tables with lots of things in them. So that's a fact-to-fact join. So now, the old way this used to work, again, so this, going back to my simple query that worked well, I had my baseball stats, those segments are allocated to servers, everything fine, and my dimension table, the teams, on every. No, I'm good, okay. The access of the dimension table and the fact table were both happening at high speed between processor and storage over a PCI bus. We like that latency, right? But the fact-to-fact join gets awkward with this new query between all my traffic data and all my smart thermostat data that I need to do in real time. The broker is going to scatter those queries to the relevant servers, and we're not going to be able to limit necessarily to very small result sets. Because typically, if we're doing a filter and an aggregation, what's coming back from the server? An aggregation, maybe a group by, maybe it's a slightly big group, but probably not that big, right? So the stuff coming back to the broker, so the broker can gather and merge those results and send them back to the client, isn't all that bad. In this case, not so, right? There is a terrible burden coming back, and this is not happening over the bus. This is over the network, which is fundamentally slower and always will be, no matter what. So fact-to-fact joins in the traditional architecture didn't work real well, so that was just bad for the broker. Anyway, the basic idea here is that now, and I'm going to give you a super hand-wavy explanation of this, what the cluster is able to do is to define some intermediate servers where batches of data can get sent back, and this is batch in the sense of the real-time execution of the query over some fraction of a second. So the filtering happens at the segment level where all that stuff is, and rather than getting thrown back to the broker, which is they are generally smaller in number than the servers, the cluster is able to figure out, here are some intermediate servers that will be an efficient place to put this data so the joining can happen there enough to be able to run the filtering and the aggregation and then send those result sets back to the broker. So the broker is getting results kind of the cardinality that it expects. And that's a very quick summary of a very exciting feature. But like you saw, traditionally, because of the way Pinot is built and the kinds of queries it's optimized for, joins were very limited. And in the next release or two, releases are about quarterly for the open source project. In the next release or two, these will be a kind of a 1.0 feature ready for production use, early in their life, so you still have to be a little bit of a cowboy, right? But it's kind of there. So a cool thing to look forward to that is not so much any elemental way of scanning less, scanning faster, scanning in parallel. It's a case where That's a hard problem, and we're trying to use the resources of the cluster in a smarter way to handle what is inherently a more expensive kind of query, but gives you more flexibility at the application level. In summary, what makes Pinot fast? We talked about it: scan less, scan faster, scan in parallel. Nobody makes a slow database, right? That's just not a feature. Everybody talks about performance numbers. That's appropriate. What Pinot is really trying to do is right now. Systems that are oriented around the processing of events and results that are facing users who are, in their interaction with their devices and their web browsers, fundamentally synchronous, and we don't like to wait for long. That's why Pinot exists. If you want to know more, everybody wants to join a new Slack workspace. Take a picture of that, join us in Slack, ask your questions. I'm there, others are there. Thank you for coming.